Thank you for this opportunity. Today I will continue discussion about monopole fermion scattering and Galan-Rubakov problem. My talk will be based on two papers. First, posted about 2 years ago in collaboration with Takeogui, and second, this summer in collaboration with Takeogui and David Tong. Let me just remind you once again what is the Galan-Rubakov problem or semitone puzzle, just everyone to be on the same page and to be self-contained. After that, I will tell you what is Fermion-Rotor system and how can we use it to resolve the puzzle. And at the end, I will make some connections to boundary conformal field theory. Basically, I will show that whatever this system is in far IR is described by boundary conformal field theory, and twisted sectors described yesterday will emerge automatically as a result of IR dynamics. Why is this even an interesting problem? I think first interesting statement about the system can be seen even in the framework of classical electromagnetism. Just imagine you have particle with magnetic charge and particle with electric charge separated by the distance r. And you ask trivial question. What is the angular momenta of this system? If you calculate angular momenta, you will find that on top of usual contributions you are expecting, there is this very interesting piece that is just the product of electric and magnetic charges and does not depend separation between them. So that means does not matter how far away you will put these two particles, this piece will never vanish. As a result, you have two consequences. First, which is trivial. When you define your angular momenta, you need to include this piece. And second, which is less trivial. As you know, representation theory for the Poincare group heavily depends on your definition of the angular momenta. And here you have a piece that does not vanish, does not matter how far away two particles are. And same time, it will vanish if you remove one particle from the system. As a result, if you write down multi-particle representations of the theory, you will find that they are not direct product of one particle representations. I think this one is itself very interesting statements, but things become even more interesting when you ask next trivial question. What happens if I scatter this, let's say, fermion on the magnetic monopole? Let me work in following limits. I will consider GATT monopole and standard model fermion, which has energy, which is much smaller than GATT scale, but same time is much larger than electroweak scale, such that I can assume monopole to be point-like, and I can assume fermion to be massless. Additionally, we know that we can deposit electric charge on the magnetic monopole. And I will assume that energy that is required to localize electric charge on the monopole, so dionic excitation energy, is much larger than fermion energy. If you study a problem in these limits, you will notice that it is very useful to do partial wave decomposition. Of course, partial wave decomposition should take into account this piece, but it has been done more than 70 years ago. We can just read all the literature. And what we will find is very interesting. Partial waves which carry J, that is bigger than minimal allowed angular momenta, that is given as E times G minus 1/2, will develop large centrifugal barrier and will be elastically reflected from the monopole very far away. On the other hand, something very interesting is happening for minimal partial waves. Let's imagine, just for simplicity, E times G is 1/2, so it is minimal monopole, and minimal J is 0. So we are talking about scattering of S waves on the magnetic monopole. In this case, you can look at kinetic term of these S waves, and you will find something really interesting. It looks like following way. Here, interesting piece is this sign of E times G appearing in front of the space derivative, which will tell you that if E times G is bigger than 0, high contains pulling going partial waves. And if E times G is, high is purely ingoing, it is already partial. If E times G is less than 0, high is outgoing fermion field. So as a result, scattering problem of the fermion on the magnetic monopole is reduced to 1 + 1 dimensional quantum field theory that is chiral. The fact that it is chiral results in very interesting dynamics, and to see this dynamics I will be even more concrete. Let's consider minimal SU5 GAT that breaks down to standard model. We know that this breaking embeds breaking of some SU2 subgroup to U1, and under this SU2 we have monopoles, what we usually call GAT monopoles. And I will study scattering of fermions on these GAT monopoles. We know that under SU2, standard model fermions form following 4 doublets. These 3 is C, U2, U2C, U1. And if you examine quantum numbers of these doublets, you will find that upper component of this doublet has positive U1m charge, and lower component has negative U1m charge. Let me just study scattering on the magnetic monopole with negative magnetic charge. In this case, by comparison with these conditions, we will find that lower component of the doublet is purely ingoing, and upper component of this doublet is purely outgoing.
Can you remind us what is this U1m?
U1m in the standard model, it is combination of it's neither hypercharge nor electromagnetism, nothing. It is some combination that I don't exactly remember, but it carries color as well as SO2. Okay.
What do you mean by carries color? Like
I mean, magnetic monopole can have color.
yeah. One of the generators, diagonal generators of SU3.
Sorry?
One of the diagonal generators of SU3.
I think so, yes.
Yeah, it's color,
Yes,
color
that is a, I don't know the change.
Yeah, there's
Yeah.
a color ice and a color
Yeah.
hypercharge, and
Yeah.
I've already fixed the gauge frame.
Yeah. Okay. So this ingoing outgoing convention plus the symmetries of the problem, which is U1m plus flavor symmetry associated with the exchange of the doublets, fixes a lot about the scattering process. For example, if you ask the question, what happens if I scatter U1 plus U2 on the magnetic monopole, you will find that only final state that satisfies conservation laws and this everything is E bar plus this 3 bar. So this process goes with 100% probability if U1 plus U2 scatters on the magnetic monopole. This is one of the processes that underlies monopole catalysis of proton decay. So if proton meets monopole, it decays with 100% probability. That is, and usually it's assumed that in the minimalistic cases, cross-section of this process is basically geometrical size of the proton. That's exactly why I care about these processes, because as you see, you have process that has huge cross-section and it's very dramatic. So we can use it to set bounds on monopole abundance in our universe. And this has been done, and most important source is following. Just imagine that Sun has been around for 4.5 billion years. It has had very large time to capture magnetic monopoles. Magnetic monopoles are basically indestructible. They are going around, catalyzing proton decay. As a byproduct, they are creating mesons. These mesons later decay to neutrinos, and this changes solar neutrino flux. So by setting bounds on solar neutrino flux, we can set bounds on monopoles. And if you look at papers, for example, by Super Kamiokande, you will find that corresponding bounds are 8 orders of magnitude stronger than next competitive bound. So if we want to understand this phenomenology, we better have very good understanding of underlying scattering process. But unfortunately, we don't, because if I ask same question, but even simpler, what happens if I scatter just one fermion, let's say positron on the magnetic monopole? I will get that final state by exactly same arguments will be 1/2. Okay. Let me D3 plus E bar plus E1 C bar plus U2 C bar plus M So quantum numbers tells me that final state should contain half particles. That is nonsense. I don't have any half particle in the standard model. So this is known as a semitone puzzle, or sometimes it is known as a unitarity puzzle, because what is really happening is that for one particle final state, actually for one particle initial state, actually we don't have any consistent final state. We can write down. And resolving of this puzzle will be one of the main motivation for this talk.
Sorry, slight question. I would have thought that the right-hand amplitude was just given apart from the factor of a half is given by a crossing of the left, but there's more leptons.
Sorry?
You have an EC on the left side and an EC on the right side. There really is also a lepton on the right side.
What do you mean by E bar, I guess?
So what is E bar?
E bar
I just would have thought naively up to the fact that it's not naively in the Fock space that like the ingredients would be obtained from the crossing with the.
I mean, they should be able to conserve electric charge.
Yeah, maybe the question is how is electric lepton number conserved on the left? It's not.
Lepton number is validated on the
Yeah,
left.
it's very
And on the right, I mean, lepton number is still not conserved on the right because you
Yes.
have this factor of this half, right? So
Yes.
somehow invoking lepton just number conservation is wrong. Anyway, it's a naive confusion. I'm sure we talk about.
I'm not sure.
What is E bar?
What's E bar?
Yeah.
I mean, it is, let me see, it is right-handed positron.
Yeah, I guess EC is the left-handed biform made out of the right-handed
Yes.
guy, and the E bar is the left-handed electron where you take conjugation.
Yes, exactly. Yeah, exactly. Yeah. Okay.
So, whole point is to somehow resolve this puzzle. However, I mean, S5 is too complicated. Instead, I will consider some very simple toy model that retains all of the important physics that is important for the scattering process, but same time it is simple enough that we can really understand what's going on. This model is known as a Fermion-Rotor system and was introduced by Polchinski more than already 40 years ago. Uh, 84, I think. And the idea is actually very simple. Idea is that we are saying that E times G bigger than 0 is ingoing, E times G less than 0 is outgoing. Instead of thinking ingoing and outgoing, let's think about quantum field theory on real axis, such that I have monopole at the center with some size R0 that will be taken to be 0 at the end, and I will map ingoing direction at negative side of the axis and outgoing direction at positive side of the axis. So, scattering problem we reduce to the problem of propagation of the field on the real axis, where you have some impurity at the center. I will introduce single right-moving fermion field for each doublet, such that if it is evaluated at the negative side of the axis, it corresponds to lower component, because lower component is ingoing. And if it is evaluated at positive side of the axis, it corresponds to upper component of the doublet, because it is outgoing.
This lower, this negative, positive x, is it just so that you can draw nice pictures?
Exactly. Exactly. It is just to draw nice pictures, nothing else, because we know that in 2D I can make like left mover to right mover, nothing else. There is nothing more, yes. But it comes out that in the calculation it is simpler at some point. Okay. Now idea is that let's do following. Instead of thinking about 4 doublets, let's think about n doublets, n psi i's, and write down the theory that conserves all of the same symmetries that standard monopole fermion scattering problem does. These symmetries are S1 associated with exchange of the doublets, plus U1m associated with basically gauge symmetry. But here I'm working in zero coupling limit, so gauge symmetry will become effectively global symmetry. So writing down something that conserves S1 is extremely simple, but writing down something that conserves U1m becomes a little bit hard because we embed upper and lower component of the doublet in same right moving field, but upper and lower component have different U1M charge. As a result, when U1M acts on the monopole, on the right moving fermion, it transforms non-trivially with this fx function. Perhaps I should write tx. Whereas this fx function is nothing more than regularized step function. It goes from -1/2 to 1/2. And size is, of course, R0. So this means that we cannot naively write down the theory just in terms of size that will conserve this, but we know what to do when some symmetry becomes local. We can just introduce gauge boson. However, here things are a little bit simpler. Actually, special profile of the transformation is fixed. So it is enough to introduce just quantum mechanical degree of freedom, rotor, that transforms under U1M with following way, just shifts. Now it is already possible to write down the theory in terms of rotor and n right moving field that will conserve all of the symmetries.
Sorry, can you say the motivation behind introducing alpha degree of freedom again?
Yes, I mean, I want to. Okay, there is very deep physical motivation. It will describe dions in my theory. But right now I want to say, because I want to make link with boundary conformal field theory, that I'm introducing it because I want to write down simple local Lagrangian that will conserve U1M. And here I see that under U1M I have some crazy transformation that is space dependent. Now, I mean, it's basically gauging the symmetry, right? Global symmetry become local. So I introduce something like gauge boson.
Okay. It's a formal machinery to have a manifestly local gauging variable.
Yes, but at the end we will find that it describes dionic excitations of the monopole.
Yes.
But is this, maybe can you comment, because Clay yesterday said that what he did, it could not be done. I think he did say something. We had to go through the language of boundary states.
This will flow to boundary states.
No, but even before it flows to boundary states, you actually say that there is an actual Lagrangian.
Yes, there is actual
There is an
Lagrangian.
actual Lagrangian in terms of
Yes.
there is an actual path integral that we can write down. Which
Yes.
And you can explicitly show from this path integral that it flows to boundary conformal field theory in far IR limit. I will identify twist operators and find exchange relations and things like that. I mean, story will be basically reproduced. Okay. And Lagrangian looks like what you would imagine it looks like. So I have just the x, let's say, kinetic term for the fermion. It is right mover, so it's just dt plus dx, plus I have coupling with the rotor, but special profile of the coupling is fixed by the derivative of f function. And I will introduce kinetic term for the rotor as well, and kinetic term I will tell you why we need in a minute. Before that, let's look at following, that coupling of rotor with fermion current is fixed by the derivative of f function. But f function is regularized step function. So this will be regularized delta function. That is fx. So rotor couples with fermion current only on the monopole, or if you like, only on the boundary. Now, first,
Why is it called the rotor? Sorry, is it because it's on a circle?
yes, because it is particle on the circle. Yes, but it was, I think, first identified in the framework of Tuft-Polyakov monopole. This degree of freedom, something like that, lives here. Okay.
So, yes.
Is this the most general Lagrangian you can write with this compatible with symmetries, or you are neglecting some terms?
I think I would look at this as a toy model, not as a full UV description or something. I mean, I can imagine that you can have extra terms here. But we will see that physics that this reproduce is extremely similar to monopole fermion, and it describes the physics very well. Okay, so what you can show is that this Lagrangian first is classically invariant under the symmetries. You like it to be invariant, and second, you can find that any relevant anomalies cancel. Additionally,
Sorry, I thought that you can just start with some UV completion of the monopole. That's all.
you will get something similar.
Reduce, and then you get this.
You will get similar.
Sync.
What do you mean by similar?
I think, if I remember correctly, here is little bit different coupling. But at the end, when you solve both models, it will reduce, give you same boundary conditions. That is only relevant part in this.
In what sense this solves the semiconductor puzzle? What does this add to the semiconductor puzzle?
Sorry?
What does this add to the semiconductor puzzle?
I mean, I will show you that here as well, there is semitone puzzle, and it is resolved. And here as well, there is twisted sectors. And this automatically emerges as a consequence of dynamics.
So this solution also in the end you have the picture that the particle.
Yes, exactly.
Particle has some trading.
Yes, exactly.
Trading cuts.
Yeah, exactly. Okay. There will be exactly the same picture. Yes.
So you can check that symmetries are here. And you can also check that if you define fermion current, which corresponds to just global rephasing of all of the fermions with same phase, following current, let's call it J, we have ABG kite the anomaly with rotor. Now you can do very easy manipulations, and you will find that corresponding charge before and after scattering corresponds to n over 2 pi delta alpha. So non-trivial winding of alpha breaks fermion number. So in this theory, you have instantons that violate fermion number conservation. That is very similar to what you have in Galan-Rubakov effect, when you know that baryon number is violated by abelian field configurations on top of magnetic monopoles. So we are reproducing all of the physics that is relevant for fermion monopole scattering. Now let's see what is the physical meaning of alpha. To see that, it is enough to write down charge operator associated with U1m, and you will find following. Here, this second term just corresponds to charge associated with fermions, and first term corresponds to conjugate momenta associated with alpha. So if you give alpha non-zero conjugate momenta, you will deposit charge on the magnetic monopole. So alpha corresponds to, alpha is basically effective description of dionic excitations. Additionally, you can easily show that if you give order 1 pi to alpha, energy of corresponding excitations will be proportional to 1 over I, where I comes in kinetic term. And we will work in the limit where this is much larger than fermion energy, such that we cannot excite the dions. But you can see very easily that here also we have semitone puzzle. And this is just because how we constructed the system. So we have psi field such that left to the monopole, under the symmetry group, it transforms in representation n-1, and right to the monopole, it transforms in the representation n+1. Now you can ask the question, what happens if I scatter n-1 on the magnetic monopole? On the right-hand side, you cannot write with any linear combination of n+1, 1 n-1. And same time, we are saying that dionic excitations are heavy, so I cannot leave back -2. I mean, I cannot do that. -2 cannot be localized on the monopole. Now, I mean, situation is very confusing because I am giving you the Lagrangian that's extremely simple. It is just particle on the circle coupled with the fermion. and it has a semitone Basel. That means it seems we have some problems with unitarity, but that cannot be true. It's just too simple Lagrangian. You can check that corresponding Hamiltonian is Hermitian, so everything should be going well. So what's going on? What's going on? Probably you already guessed that during all of my talk I have been extremely naive. I have never quantized this theory, never have obtained one-particle spectra, and somehow I am still talking about scattering, because I am implicitly assuming that fermion field content of this theory is in one-to-one correspondence with one-particle spectra. That is usually a very good assumption in many quantum field theories, but we are aware of quantum field theories where that is a terrible assumption, especially ones with strong non-perturbative coupling. And here, as you see, rotor couples with monopoles non-perturbatively. So whole hope is that if I do proper job, quantize this theory, obtain one-particle spectra, there is chance that I don't have any semitone Basel at all. And that is exactly the case, as we will see in a minute. But of course, when you have non-perturbative coupling, it is very hard to quantize the theory, but here we have very large simplification. If you look at Lagrangian density, it looks like following way. In incoming direction, you have basically free fermion. In outcoming direction, you have basically free fermion. And in between, you have the region where you have strong coupling with rotor. So what this does is that you can actually solve path integral of this theory for many correlation functions. Basically, every correlation function we tried to solve was given with following form and could be connected with the correlation function given with following form. When you have some correlation function in the background of, sorry, not in the background, in the existence of the rotor, you will first pretend that there is no rotor. Theory is free. Write down all possible weak contractions. Then you will be left with path integral. There's basically product of free weak contractions and some path integral over alpha. Then in every case we checked is always Gaussian. And you can actually perform and calculate every correlation function you like. This formula was derived for arbitrary number of fermions in this original paper by Polchinski, and it is basically trivial to extend with rotor insertions as well. Now,
Yes.
I have a basic question. So
Yes.
alpha is a periodic variable.
Yes.
Does the Lagrangian respect?
Okay.
no, it does not. You should be very careful with boundary states. You should consider correct theta vacuum, and then it will be automatically restricted to periodic value. If you don't do that, you will find that you don't have correct cluster decomposition properties of correlation function. But yeah, yes, that's the case, yes. You should be very careful between what states you are calculating this.
So I should take this Lagrangian with a grain of salt.
Yes, exactly. So you need to be very careful that alpha is actually periodic. So I should always evaluate correlation functions between correct theta vacuums. Yes. But that is actually one of the very important questions because...
Sorry, what does that mean, correct theta vacuums in this Lagrangian?
I mean, you will find that if you naively do calculation, correlation functions you will find does not give you correct cluster decomposition property because...
This is a very fancy answer to the question of whether that Lagrangian respects the periodicity of the scalar. So...
Yeah, it does not. And I'm saying that you should evaluate it in between these states with n theta, where n is topological angle. N is just topological angle.
So can you restore the periodicity at the level of action or not?
I don't think so. I'm not sure, probably, but that's a simpler way. Because what you can do is that you can evaluate correlation functions between configuration where alpha does not wind. Basically, it is zero instanton sector, but you are doing full calculation fully non-perturbatively. It contains configurations that wind up and down, and then you do cluster decomposition. and it will cluster into two instant and anti-instant sector. This is like common trick done in multi-Flavor-Schwinger model. And
What about replacing alpha by sine alpha?
I don't know. I have not tried, so I'm not sure. But this kind of way, it reproduces the periodicity, and as we will see, it will reproduce current bubble.
But I don't understand how you can compute in that kind of state if the action is not invariant under.
I mean, I will compute between the states where alpha goes to itself first.
The states where alpha goes to. So the states are
It's
labeled by
getting-
hand.
I mean, like path integral boundary condition goes to itself, and then to cluster decomposition. I mean, it's technical things that usually is worked out in two-dimensional QEDs, and this gives you correct instanton structure and things like that. So it is not something that only happens in this model, like. But yeah, I mean, I don't know explicit ways. That would be very good to have explicit ways that alpha is periodic.
Sorry, is this sheet by 2 by a gauge symmetry? Or
Gauge symmetry.
just the periodicity of alpha?
Yes, it is large gauge transformations.
Basically.
Right. So
Yes.
then why does this make sense at all? Like, the path integral, won't there be an issue?
Sorry?
Won't there be an issue in the path integral?
There will be issue.
Yeah, because of you have some zero model of alpha or something.
I don't have any zero notorial.
Yeah, I'm not sure. Yeah, okay.
Can you explain a little more how you get this factorized formula? You have
Yeah. This factorized formula. Okay, so that was what I was talking about. So this factorized formula is a little bit technical, but actually it is not what I wrote. It is what is given in the original paper. But the idea is that you start with, let's say, start with a correlation function that contains same number of fermions and fermion Daigers. Okay? And then you have path integral over alpha and psi. And your action looks like something like psi Daiger covariant derivative of psi plus I alpha square over 2 plus you will introduce corresponding currents you will introduce corresponding currents for each I, and you do basically manipulation to diagonalize this. When you do manipulation to diagonalize this, here you will get something like, if I remember correctly, you will get something like GI inverse of free propagator, and it is dressed with some combination of exponential function of alphas, Ji Daiger. Then when you take the derivative from these propagators, you will get 3 Weeks contractions. And from this kind of things, you will get path integral over alpha. Okay. I mean, this is also like technique that is known from Schwinger model. This everything is even older than Polchinski's paper.
But where's the miracle that you will get a Gaussian integral over alpha?
I don't know. It just comes out always Gaussian. There is nothing more. Okay.
So sorry, is it because the bosonized theory is free? Like in the Schwinger model, if you bosonize it, it is free.
I'm not sure, could be, but I don't know what is reason. But if you do calculation, you always get Gaussian. At least like what we tried. I mean, it could be that there is correlation functions that are not Gaussian, but what I need is Gaussian.
Is it just because you have conserved the U1 in the correlation function, so you do a field definition that absorbs this phase, so it just removes it?
Yeah, probably. So yeah, exactly. Yes, because I can remove by field definition. Exactly. Yeah.
If you didn't conserve the U1, then it wouldn't be.
Yeah. Okay. Yes. Okay. Okay. So now the idea is to look at this thing and directly try to read off one particle spectra of the theory. Okay, so let's start with looking at 2-point functions. Let's look at 2 fermion insertions. If you have following correlation function such that both fermions are inserted at one side of the monopole or other side of the monopole, you will always get just 2-point function for the wild fermion. That, of course, corresponds to the fact that, as we said, it is free theory this way. Now, if I do following way, such that one fermion is inserted one side and another is inserted another side, this is 0. This also corresponds to the following fact that we know psi I, left and the right, have different U1M charge. By charge conservation, they should vanish. So everything seems consistent. Now, before going to semitone puzzle, let's look at other Galan-Rubakov processes.
So in the first case, what is the physics? You're just throwing in the particle and antiparticle and absorbed into the monopole. Is that the physics what's happening?
No. It is just propagation. It never goes to monopole. It is just 2-point function left to the monopole. I mean, you create here, absorbed here, before going to a monopole. Yeah. Okay, now let's look at non-problematic Galan-Rubakov processes. Let me fix n equal 4. And let's study scattering of 4 and 3 on the monopole. Just 2 particles. We know there is no semitone puzzle here. Then you can really identify non-zero correlation function, which is following. Where you have insertion of 2 psi's here, 2 psi's here. If you map this back to standard model, you will get U1 plus U2 plus M goes to U, same thing, E bar plus this E bar plus M. And with this way, you can reproduce all of non-zero Galan-Rubakov processes, all of non-problematic Galan-Rubakov processes. So we have effective description of monopole fermion scattering. Now let me go to the process where we have semitone.
Sorry, before you can. So I thought you knew how to compute correlators so that are vanishing global charge.
Yes, I know also how to compute these ones. And the idea is, okay, that's a good point. Idea is what I was talking about theta vacuum. If I have this, I will calculate 8-point function that has psi 1, psi 2, psi 3, psi 4 as well. And then I will take time such a way that it clusters into 2. And then I will just read off what square it is. Up to phase I will calculate, but full phase I don't care. Also phase can be exponential in theta.
So this is something you can actually compute and check if it works.
Yes.
Well, Rubakov did it too.
Rubakov did it too, yes. It is not me, exactly. And Polchinski did it too. I mean, it's not, yeah. Okay, now let's look at correlation functions that corresponds to semitone puzzle. N is still generic, and I will study scattering of one fermion on the magnetic monopole. I have one fermion at the left, ingoing direction, and I have some operator of the outgoing direction. Now, you can convince yourself very easily that any operator you can write here which just contains local fermion insertions, gives you always 0. That just follows from the symmetries. That is because we have semitone puzzle. However, of course, this cannot be true because if every this can be true, but not every correlation function is, I mean, you cannot have theory where every correlation function is 0 because that means it is not unitary. So there should be correlation function that is non-zero. And that's true. We have identified this correlation function. And trick is that you should use rotor to do that. You should use rotor fermion insertion, how you would do it. But now this does not conserve C1M. You should insert exponential of rotor to conserve U1M. But you should insert rotor at very specific time. It corresponds to light coin of the outgoing fermion. In this case, you can show that this correlation function is not only non-zero, but it saturates unitarity. Meaning that if you calculate this, you will get nothing more than propagator for free whale fermion. So, whatever is, when one particle scatters on the monopole, what you get back is something that is created by this non-local composite operator with 100% probability. Now, what is this?
Sorry, does alpha live only at x equals 0?
Alpha is just quantum mechanical variable. Yes, it lives everywhere. I mean, it's quantum mechanical variable.
So t prime minus x prime is an argument, or you're multiplying that to the alpha?
Argument.
Argument, right? Okay.
Well, what is this? So you throw in an electron, you come out as an
I will show you that what
and
is
then
now.
plus what this is.
Okay, I will show you exactly now what it is. So to see what it is, first I will look at the, well, at the end it will be exactly twist operator, but I will show you how it is twist operator. So, first let's look at symmetries to identify what is this guy that comes out. So, under SUN, exponential is, let me call it O or something. OI, T prime X prime. Under SUN, psi I has quantum number n, so it is fundamental, and exponential is singlet. Under U1M, psi has quantum number +1 because it is evaluated right to the monopole, and exponential shifts under U1M, so after normalization it has charge -2. So it has U1M charge -1. So at the end, quantum numbers are n-1, as it should be, because we are trying to solve the problem where this symmetry should be conserved. Okay, that's completely trivial. But what is non-trivial is that if you take this seemingly non-local composite operator, which contains fermion as well as rotor, or if you like, dionic collective coordinate, you will find that corresponding two-point function is nothing more than two-point function for free whale fermion. Meaning that this operator just creates one particle fermionic state with quantum numbers n-1, even though you never had corresponding fermion field in your theory. So the trick is that final state is created by combination of fermion and rotor. This, of course, solves the puzzle because what comes back when you scatter n-1 on the monopole is that actually n-1 comes out, just like story that was said yesterday, up to twist that I will mention in a minute. But actually, before that, I think here something even more interesting is happening. If you look at fermion field content of the theory, you will find that it is n-1 that is ingoing, it is n+1 that is outgoing. If you look at one particle spectra, of the theory, you will find n-1 goes in, n+1 comes out. They are interpolated by just fundamental fields. n-1 comes out that we just found interpolated by this operator, and there is corresponding other similar operators that interpolates ingoing n+1. So we started with a field theory that looks like chiral, and we, by just consistency of the scattering, force it on us to have these extra states. But there is very important caveat. These states can be only populated by some manipulation of the monopole, for example, scattering. This, of course, solves the puzzle, but same time, I think by itself is very interesting phenomenon.
So is this the local physics? It's as if you have this.
It is not quite
but then you just excite the dion at the core of it. Somehow you just modify.
I don't think you excited dion in the core.
No, you don't excite a dion in the core. As we will see in a minute, what you will excite is twist operator. What we will excite is twist operator, because alpha is strongly coupled with the fermion. It is, how can I say? It is, how can I say that? It's just, it doesn't make sense to talk about just psi, just alpha. They are strongly coupled to each other. from equation of motion, alpha will take part of the psi. And we will have that basically same story that was said yesterday. It is just from here, you can see from path integral.
And you're going to describe how this can be interpreted as a twisted alpha.
Yeah, I will describe, how it can be interpreted.
So in the IR you can use that language, but here you have a local Lagrangian. So what is the answer in here, like without flowing to long distances?
I mean, here at the point of 2-point functions, I see that I have just one particle excitations. If I go to higher point functions, I will find branch cuts in the higher point functions, because I'm working in the limit where I goes to 0 all of this calculation. So basically, dions are infinitely heavy, and what stays is only this twist. And this will just appear in correlation functions. I don't think there is any difference in IR between, at least that's what we believed, that there was no difference in IR between Fermion-Rotor system and BCFT. Not only here, I will show later that it can be done in.
So what does the rotor story add to the CFT story?
Well, I think story was different. First, we did not know that it was CFT. We wrote first paper. Then we realized it was BCFT, and we wrote second paper. Now I'm giving you story, just different direction.
But the result is the same.
And this result will be the same, except that we will see VR from it might be coming from UV, right?
How do you?
I mean, for example, like alpha is dionic. Alpha describes dionic effective coordinate.
But it's a little bit weird, right? Because you're not exciting the dionic.
Yeah. But it is strongly coupled. It somehow takes part of the fermion field. So, yeah, I don't know.
I just want to make sure you're not giving a UV completion to the twister story.
No. I mean, it is UV completion is a twister story in the sense that if you start with this theory and consider RG flow to IR, you will find twistor story. And in UV, it is very well defined theory. It is just, if you have high energy, it is just fermions scattering on monopole. There is dions which gets excited. And when you go low energy, lower than dionic excitation energy, twistors will appear. Twists will appear. But at low energy, you cannot see the difference because they are same theory, exactly. So there cannot be anything extra, otherwise they will not be same. Okay. So now let me move to make the connection with boundary conformal field theory. And I think we had somewhere this picture. Okay, I don't have a picture. So, our situation was following. When I look at Lagrangian density.
Sorry, can I just follow up on that question? One. So, what states is alpha acting on? So, I mean, if alpha lives on the line, this quantum mechanical line, and you have already restricted it to not excite the dion states.
Yes.
Why is it not just a trivial operator?
Because it takes from the equation of motion part of the fermion field. Phase of fermion field gets entangled.
Why isn't it just stuck in its vacuum? If you already say that I take the splitting between the ground state of the alpha sector and the first excited state to infinity, well, why is it not just stuck in its ground state and it cannot do anything?
It cannot stuck the ground state because just
imagine that take this Lagrangian and remove alpha. If you remove alpha, it does not conserve you 1m charge. If alpha is there, it conserves you 1m charge. Does not matter that excitations are heavy. So it should play some role in IR dynamics. And this everything is happening because this is not weakly coupled theory. You cannot do any perturbation in this expansion.
But didn't you already take the splitting? I mean, you took I to
zero. Yeah.
0 to scale this splitting, right?
Yes.
So, but why can't we just integrate out alpha then?
You can integrate it. I will integrate it out in a minute.
Why isn't it stuck in its ground state? I guess I'm confused.
It is not stuck. I mean, I will integrate it out, and when I will integrate it out properly, I will get just twist operator.
Maybe it's a statement that there's a trivial ground state and there's like a twisted sector ground state.
Yes. Exactly.
And then scattering the monopole
just gives you to another ground state that is mediated by alpha, but at the end, alpha will be not in our expressions. Alpha will go away and it will change with those twist operators. It is just this way you help us integral that you can evaluate over alpha. But at the end, of course, because everything is heavy, you should go to boundary conformal field theory. Exactly, because our system looks like this, right?
So is it similar to when you integrate alpha, it's not you just get a free Fermion, but there is also topological degree freedom left out in the IR, and that plays a role of it.
Yes. Because this theory looks like following, right? I have theory of free fermions. I have theory of free fermions. And in between, I have a region where I say it couples to alpha. But as we saw, only purpose of this region was to just basically conserve the symmetry, help us to conserve the symmetry. And as it was already said here, this negative and positive difference is just choice. I can flip my x-axis. I can fold this system. Instead, I can consider situation where instead of negative axis that is ingoing, I have left movers that is ingoing, and I have right movers that are outgoing. And instead of this strongly coupled region, I have just boundary. And I will ask boundary to conserve the symmetries that I'm trying to conserve with Fermion-Rotor model. And you see that this is similar formulation because here I just introduced degree of freedom that was conserving some symmetry, but then I say corresponding excitations are heavy. But whatever is left over should still conserve the symmetry. So.
But you say this is a strongly coupled theory.
Yes.
How far is it? So if that's the case, how?
This is also strongly coupled theory because boundary.
In what right, other than symmetry, in what right you can say it's a property of freedom? You can say you can integrate it out. If it's strongly coupled.
I'm doing all of the calculations non-perturbatively. So
you integrate out the non-perturbatively?
I'm integrating all the I'm doing any perturbation expansion. I can perform every path integral by itself. So I'm not doing any approximation in this calculation. Of course, I cannot say it is heavy that it will get integrated out. No. Okay. So, and this should be similar because boundary is same thing, right? We are saying that there is some magical boundary that conserves the charge. But you can imagine there is some substructure that helps you to conserve the charge. That's exactly how this looks like. And good thing to ask question like that, as we saw yesterday, is that now you are asking the question, I have some chiral CFT, and I'm trying to put it on the manifold with boundary. Now I can apply all of the imaginary of boundary conformal field theory. And we already discussed today that there was a proposal. What happens in this case? There was a proposal, I think already 3 years ago, in this paper. By Wambist, Smith, Del Mastro, Komargotsky, and Donk. And we already discussed this, but let me remind you what is a proposal. Proposal is that when you throw left mover fermion on the boundary, what comes out is right mover fermion that lives on top of topological line. And we saw yesterday in Clay's talk that basically S-matrix calculations supports the fact that this actually saturates unitarity in this case. Okay, so for the purpose of my talk, I will little bit rephrase this proposal that is equivalent. I will say that final state is created by right mover field and some non-local twist operator, which has following properties. Scaling dimension of whole thing is 1/2. You see that that is equivalent to statement to say that in Fermion-Rotor system we have these non-local composite operators that have 3 2-point functions. It has quantum numbers n-1 under the symmetries, but again, this is trivial because we are trying to conserve the symmetry. If it is not n-1, we are doing something wrong. And on top of this, we have this mild non-locality that if you drag psi tilde across the topological string, there is a branch cut, and it will pick up some phase. But we can say this more convenient way. And more convenient way is following. We can say that twist operator actually commutes with ingoing left-moving fermions, commutes with outgoing right-moving fermions, and fermion sits somewhere outside of end of the topological string. But it does not commute if psi tilde sits somewhere here. So we have, in this case, we have non-trivial exchange relations, where exchange relation is given with following.
So can you comment on the physical meaning of all those three conditions you're requesting?
Which one?
Like this twist operator commute with the psi.
That's exactly the same as saying that if you drag it across topological strings, there is a branch cut. Yeah, because if you are commuting here, you are crossing here string. If you are commuting, you are crossing here. And ingoing, we know it commutes. Okay. Yes. This is, yeah. So correspondingly, we have following exchange relations. T, that is labeled with this, will commute with ingoing. Let's call it Y. It will commute also with outgoing fermion.
Is T a line or a local operator?
Sorry?
Is T a line or a local operator?
I mean, when I'm talking about this operator, I'm abusing notation. Look here, it is like end of the operator, local operator. Yeah. Okay. And this happens, as we said, if operator is outside. So if I have, how can I, okay, which one was X? If Y is bigger than X, so it is outside. But if it is not bigger than X, you will exactly pick up this branch cut phase. X, if Y is less than X. Now, our claim is that this solution is actually equivalent to Fermion-Rotor solution. And, okay, it went out. You already see, okay. You already see some equivalence here. We have some non-local operator, line or whatever, it is non-local operator. Same time, it carries scaling dimension 1/2, so it is just one particle state, up to twist. And we see here, quantum number is same, and on top of this, we have twist. So, first three things already agrees. To make sure that we have really describing same physics, we need to find if there is a twist operator in this theory, and if it has correct commutation relations. You would probably guess that first candidate for the twist operator is exponential I alpha. It even sits at correct place in the operator. If you look at it, if you look at the operator, we are writing exponential I alpha
sorry, I'm confused by that answer. E to the I alpha is some operator that lives on the line, and the T that you're gunning for is some extended topological line that could move, that can be anywhere in the bulk of this 1 plus 1D system. E to the I alpha maybe could be like the endpoint of the line.
Yeah, it is endpoint.
Okay.
It's endpoint, yes. Yes.
So also T is what, like a Zn symmetry generator only acting on the outgoing fermion?
Yes, yes.
It doesn't acting on the incoming fermion?
Yes, yes.
Okay.
Yes.
And when you say alpha is a ending point, are you sort of doing, do you mean that there's a certain topological degree of freedom leading on the T, and then alpha is sort of edge mode of that? Is that what you have in mind? Or?
Well, you're going to show us how do you get data.
Yeah, I will get exactly this relation for alpha. Yes.
So yeah, in the interest of time, let's keep questions for after Vazha.
I'm almost done, so.
Very bit over.
Yeah.
Please.
Yes. Okay, so idea is that twist operator is exponential I alpha t minus x dx. And how we are gonna show this? We are gonna calculate commutation relations. To calculate commutation relation, it is enough to just obtain one commutation relation, which is alpha t minus x commutator with psi dy. So how you obtain this? You look at the equation of motion for alpha, solve it in terms of fermionic currents, and now you know commutator between fermion and fermionic current. And with this way, you will find that this commutator is 4 pi over n theta y theta x minus y times psi I dy. Meaning that it exactly has the form that you are requesting. It commutes with ingoing fermions because if y is negative, so if it is ingoing, it is 0. It commutes with outgoing fermions if outgoing fermion lives outside of end of the topological line, because if y is bigger than x, this is 0. And it has non-zero commutator only in between. And you can work out commutation relation, and you will exactly get this. So it is twist operator, but just in a minute, I will say that you can do more. What you can do is that you can actually bosonize the theory. I will introduce one ingoing and one outgoing fermion, boson for Fermion-Rotor system, just exactly same way it was introduced in BCFT. And then I can look at the equation of motion, and I can actually solve for alpha. When I solve for alpha, I will find that exponential I alpha t minus x is actually given as exponential minus I 2 over n sum over I high tilde I. That is exactly the relation for twist operator that was obtained in the original paper. So this way, what's going on is following. We introduce alpha to conserve U1M charge in the system, but we found that corresponding physical excitations are heavy, so they should decouple. But alpha should guarantee conservation of charge in this system, because if you remove alpha from the Lagrangian, it does not conserve charge anymore. So there should be something beyond just heavy excitations connected to alpha, and it seems like this something is twist operator. And with this way, Fermion-Rotor system, infra IR flows to boundary conformal field theory, and that's why two solutions seem similar, because they are the same. And actually, we have shown this fairly large class of boundary conformal field theories. You can introduce some number of alphas, some charge assignments, as long as you will make sure that it is anomaly free. In the IR, you always will get by BCFT. There will be twist operators that are always given in terms of exponential I alphas, and they have exactly exchange relations and forms that is predicted from boundary conformal field theory. So I will end with this, and if there is questions.
Great. We have time maybe for one or two quick questions. Yeah.
Yes.
So this twist operator T, or line operator T, this only becomes topological on the limit that I goes to infinity, right? Or to
0, yes. Yeah, exactly. I think it could be very connected to what you were saying yesterday about memory effect.
Yeah. And also like, so the commutator of alpha dot, for example, with t, you could also talk about, and that would be like essentially a shift in that by unit, I think.
Yes, I think something like that will be. You should be very careful with I expansion, and there can be I over 1 over I, and yeah.
So,
Yes.
and that equation you have written, last equation you have written e to the I alpha in terms of chi tilde.
Yes.
Would that be sort of a work realization of what naively appears to be localized on the boundary?
Exactly. Yes. Exactly. Yes. Yeah.
Okay, let's thank the speaker again.